Hello guys, welcome to my channel. So in this video we're going to look at exponentiation and various methods of that, right? So we're also going to look at modular exponentiation, but that is going to come at the end of the video. So that is one of the most optimal way to do this process, right? Now before we do anything, let's try to understand what exponentiation actually is, right? So it's very simple. I mean, if you've done maths in high school, you know that if you raise any base number to a power, let's say 5 raised to the power 2, that is exponentiation, right? So that's it. So you know what it is. And we're basically going to try to achieve the same thing in this compiler, right? So it is clear now. Now there are various methods to do this. Some are more optimal, some are not that optimal. And the first and very easy method to do this process will be the iterative way, where you actually try to run a loop from 0 to y, and you multiply a result variable with x, y times, right? And then you return the result. So let's try to implement this. It's very straightforward, and let's call it power, I don't know. And x would be our base number, and y would be our exponent, the power. Right. So let's have a result variable which is going to be 1 because it's the identity. I mean, we need something to multiply x with and return the result. So we're going to run a loop now for y times, because x is supposed to be multiplied with the result y times, right? And result multiplied by x, and we're just gonna return result, and that's it. So let's try to understand it. I mean, it's very straightforward. So we first declare a variable just to hold our answer. We declare it and we say it's 1 because it has to be multiplied by something, and if we set it to 0, it's gonna just be 0, right? Very simple stuff. And then we run a loop y times, and basically we're multiplying x with result y times. So that's it, and we're returning result, right? So it's very simple, and to kind of visualize it, the result is 1 at first, and then we're multiplying. Let's try to do it first. Let's try to print something. So let's check if it's working. Power of 2 to the power of 5. Let's run it, and it should give us 32. Sorry, it's y. And let's run it again, and it is 32, right? So what did we do? So first it was 1. Result was 1. And then we multiplied 2. And then again we multiplied 2 because x is 2, and then again we did it 2. We did it for y times, right? And then we return the result, right? So very simple. So it works for the most part, but it's not the most optimal way, and you can definitely improve on this. And we have a better approach to this, and it has a time complexity of log n. And by the way, this one has a time complexity of y, of just big O of y, right? Because we're gonna run the loop till y times. And what if y is really huge, like 1,000, let's say, right? So it's very not efficient. So we gotta look for a better alternative. And that's why we're gonna look at our next slide. And yeah, this is a more optimized version. So we're not going to look at the code that much, but let's go through it anyway. We're going to code it in our compiler to try to understand it in a better way, right? So what we're doing in here is we're taking the result again, and we're declaring it and initializing it with 1. And now we're running a loop, and we're saying that as long as x is still there and it's greater than 0, we're going to check if the number, which is y, which is the power, if it's odd or not. If it's odd, then we're just going to multiply x with result. Remember last time we were multiplying x with result every single time. We're not going to do this every single time. We're just going to do it when y is odd, and we're going to see how it works, like, and how it actually kind of functions out. But then we're going to keep divide y by 1, I mean by 2. It's basically right shifting y, and if you have seen my bit operators video, you know that how right shifting works and whatnot. So if you haven't, just check it out. Link is in the description. Now then we're just multiplying x with itself, and we just keep on repeating it until x is no more, right? It's not greater than 0 anymore, and we then return the result as always. Now let's see how it works. So we see two things in here, right? So this is very simple. We're just going to multiply the result. We're just going to add up the result after we hit an odd power. So that is very simple. But in here we're doing two things. We're dividing, in each step we're dividing y by 2, and we're multiplying x by itself. So let's try to prove one thing, or let's just try to check one thing out. So let's say n to the power of y, any number n to the power of y would be equal to n squared to the power of, this is 2 by the way, to the power of y divided by 2. Right, so these are the two same things. So if you simplify it, it's just going to be the same thing, because you just multiply it by 2, you'll get divided, and you'll get the same thing, which is n to the power of y. So we know this, right? Now we can leverage this in our case, and that's what we're doing basically. So in each step, we're dividing y by 2, so you see y by 2, and we're kind of increasing x exponentially. So we're multiplying itself by we're just multiplying x with x, right? That's what we're doing. So in each step we're basically converting this to this, and that's how we make our function run faster and we reach logarithmic time, because in each step we're kind of clearing our steps in half. We're just dividing it by half, and that's how we get logarithmic time. So let's try to understand it in a better way. So let's say we have 2 to the power of 100, right? We need to calculate this. So in each step, what we'll do is we'll try to increase the space number, which is 2. We'll try to increase this, and we'll try to decrease this, which is the power. Right? So in each step, what we will do is we're gonna multiply x by itself, so which is gonna be and then the next step it's gonna be 4, because 2 multiplied by 2 is 4, and we're gonna divide this by 2. It's gonna be 50 now, right? And because of the thing we proved, these two are the same thing. So 4 raised to the power of 50 is the same thing as 2 raised to the power of 100, right? We proved it in the previous slide. So then we're just gonna do the next step we're gonna do is multiply 4 by itself, which is gonna be 16, and then we're gonna again divide it by 25, and we're gonna keep on doing the same thing until we don't have any power left anymore, right? So that is very simple, right? Now 25 is odd, so we cannot directly divide it. That's why we have this line in place, that if the power is odd, and by the way, this is again bit manipulation. If you don't know how to do this, you can check out my video on this. And also you can do it the normal way, right? Like you can check how if a number is odd or not in a normal way, like with the modular operator, right? So there's that, and that's why we multiply x with the result after we get the power to be odd. So then we can transfer one power to result, and then we can just make it like, because we just multiplied x with result, now we can make it 24, and 24 is odd, I mean even, so we can now keep on doing our process, like turn it to 12, and then 16 to 16 would be 256, and it just keeps on going, and we get our result, right? So let's try to implement this now in our compiler. So let's call it power again. I mean, I don't know why I deleted the previous one, but x and y, and we're again gonna declare our result and initialize it to 1. And now, while y is greater than 0, or we can just say like while y exists, because it's C++, it works like that. While y, we're gonna do some stuff. Now, if y is 2 equals to 1, you can do it like this, or you can just do the bit manipulation and just say if y is odd, then we just multiply x with the result. And you might be wondering, what if we never get an odd number, right? Then result would just stay 1. No, it will not be like that, because at the end, if we keep on dividing the exponent by 2, at one point it will get to 1, right? So, and 1 is odd, and thus it will multiply itself with the result, right? So don't worry about that. So it works like that. And then we're doing the division, right? So we're kind of dividing y by 2, and if we want to do it via right shift, we can just do this. And then we're multiplying x by itself, so this is very simple. And yeah, I mean, this should work. And it is more optimized, and then we're going to return the result after this has been done. Now let's call the function again, and let's run it, and it should give us 32 back again. Let's do it for, I don't know, to the power of 6. And if we do it for larger numbers, it should also work. To the power of 10. 10 would be this, and it works perfectly. And now this works, but this video is titled Modular Exponentiation, right? So why is that? Now, when we're talking about exponents and when we're dealing with them, we deal with a lot of large numbers. And now those large numbers may not fit into our integers, like 32-bit or even 64-bit integers. They might not fit into that. So in that case, we need to do some modular operations on it. So that's how we make them fit, right? That's how they stay under a limit. Now, so there is a really small optimization we can do to this. It's already very fast now. It's log of y, but we can do a final optimization, and we can just add these modular operations to it, and it'll be just perfect, right? So let's see how we do this. Now let's see for the action areas. Before doing that, we might want to pass on another argument. Let's call it p, because p is going to be the number we're going to do the mod with. Now we don't have to pass on p. We can just have a standard, like we can just choose a number that we're going to do mod with, and we don't have to ask it in the function itself, but we're just going to do it because why not? So we're going to make 3 as our modular a number, like the operator number, because why not? So, and we're going to look at the action areas where the number can actually increase by a lot, and where it can be increased by a lot, where there is multiplications going on, right? Big numbers. So this is an action area. This is an action area. So we'll try to optimize it now. So it's basic. This is basically right now saying result will be result into x, right? We can just remove this, and this is the same thing as that, and now we can add a modular operator to this with p, because p is what we get from the function itself. So this is the one done, and in here also this is saying that I'm just being multiplied by myself. So this is the same thing as this. Now we can remove this, and we can add a bracket to it, and we can do modular operation on both of them. I mean, it becomes 1 anyway, but yeah, we just do this, and now it's perfectly fine, literally. So now we take care of really huge numbers, and we don't have to care about that anymore, because we just optimize it for that. So let's try to check it, and let's raise 2 to the power of 5 and let's do the model again. Let's input it as 3 and let's run it. It should give you 2, I believe. Yeah, because 2 to the power of 5 is 32 and 32 mod 3 would be 2 because 30 is the last. Yeah, 30 into 1 plus 2, so you get 2. So this is basically modular exponentiation, and you can add some more optimization to it. So if x is already like, if it can be divided by p, then you don't need to do anything, right? Because it'll give you 0 at the end anyway. So you can just be like, if x modulus p equals 0, then just return 0, right? Or you can just store it somewhere, like x equals x modulus p, and if x equals if x equals 0, just return 0, right? So, or you can just say if not x, just return 0. So we're not going to waste any time, because it's if it's divisible by p, then the modulus of it's going to be 0, and it doesn't matter how many times you multiply it with the result, it's just going to be 0. So you're just going to save that much amount of time. So I mean, let's run it again. If it is working or not, it works again. And let's try it with something like if x is actually let's say if x is 3, it's just going to return a 0 because it's not going to bother with anything. See, it is returning as 0. If we didn't add this, it'll still return as 0 because we're doing the modular function. And so yeah, that's it, guys. I hope you understood this process now, and now you can optimize the exponentiation process. I cannot even pronounce it anymore. But if you like this video, feel free to share this video, like this video, and subscribe to my channel. Thank you and have a great day.